Hello, I'm Ralph Gable of the Electronics for the Inquisitive Experimenter YouTube channel. In the last video, I showed you how to design and build a step attenuator. Now, there were some folks that wanted to see the math behind the design. In this video, I will be walking through the process that I followed to derive the equations I provided in the last video. Now, it is nothing more than simple algebra. What makes it really intimidating is the mass of the equations, but it just remains simple algebra. Now, I will put a link to the go along with the video PDF in the description if you're interested in seeing the whole process. A photo of this whiteboard is included in the document. Now, I have one important note regarding this. I am going to assume that this design is entirely devoid of reactive elements for the sake of simplicity. Everything about this design uses simple resistors and no discrete inductors or capacitors. I'm going to assume the impedance values are of the form R plus 0J, making the terms resistance and impedance interchangeable and the reactance term ignorable. If you have questions or comments, please feel free to add a comment to the video. If you find this video helpful, please click on the like and don't forget to subscribe. So I will begin with developing the mathematical foundations through a bit of circuit analysis. We begin by looking at the circuit itself. The attenuator consists of three resistors. There is a resistor between the input and ground and another between the output and ground. I'm calling both of these RP as they have the same value and exist in parallel with the signal. The third resistor is in series with the signal between the input and the output. I will call this resistor RS as it is in series with the signal. The output is terminated with the characteristic impedance of the system. I'm going to call this system impedance RO. The overall voltage gain of the attenuator is going to be AV, which is a standard variable name for voltage gain. Because this is an attenuator, this number will always be less than 1. Now, on to our foundational equations. Well, the first assumption that I'm going to make is that the impedance as seen looking into the input is the same as the system impedance, RO. Now, we need an equation which defines this impedance. Looking in through the input port, the first thing I see is the parallel resistor RP. But there is a network of resistors in parallel with RP, which consists of RS in series with the parallel combination of RP and RO on the output side. So the impedance as seen looking into the input is equal to RP in parallel with RS plus RP in parallel with RO. And we know that RP in parallel with RO is equal to RP RO over RP plus RO. Putting this into our first equation, we get that RO is equal to RP in parallel with RS plus RP RO over RP plus RO. But we're not done yet. We still have this parallel combination with the input parallel resistor RP to deal with. And that gives us this lovely equation. So when we multiply this all out and we simplify it as much as possible, we get this final massive equation where RO is equal to, on the top, we have RSRP plus RSRO plus RPRO. And then on the bottom, we have RP plus 2RO plus RS plus RSRO over RP. Now, on to the second required equation. The second required attribute of this circuit is that it has a voltage gain commensurate with the dB attenuation value we assign to it. I will bring back to your mind the simple conversion equation from dB, attenuation, to voltage gain, which is voltage gain is equal to 10 brought to the power minus the dB value over 20. For example, if we assume an attenuation of 10 dB, then the voltage gain will be equal to 10 brought to the power minus 10 over 20, which gives us a voltage gain of 0.31623. Now, let's turn our attention to the circuit. Looking at this circuit, I can see that we have a simple voltage divider. We can ignore the first resistor Rp, which is in parallel with the input, because it does not participate in the voltage divider in any way. We are left with a voltage divider input resistor, which is Rs, and a voltage divider output resistor, which is the output parallel resistor Rp, in parallel with the output load resistor Ro. This gives us this equation for the voltage gain of the attenuator. Voltage gain is equal to Rp in parallel with Ro, all divided by Rs plus Rp in parallel with Ro. And we already know that Rp in parallel with Ro is equal to Rp-Ro divided by Rp plus Ro. So this becomes the voltage gain is equal to Rp-Ro over Rp plus Ro divided by Rs plus Rp-Ro divided by Rp plus Ro. When multiplied out and simplified as much as possible, I get this lovely massive equation where voltage gain is equal to Rp-Ro divided by Rs-Rp plus Rs-Ro plus Rp-Ro. But there's a nasty term in both the Ro equation that we just got and this AV equation, which really muddies the mathematical waters because it contains both of our unknowns. We simply have to get rid of it. Well, take a look at both of these equations. Do you notice this Rs times Rp term in the middle of this mess in both equations? Now, we remember that two things that are equal to the same thing are also equal to each other. So let's solve both of these equations for the miscreant Rs times Rp term. Now, without going through that whole process, here are the two equations. Here's the one from the Ro equation, which tells us that Rs times Rp is equal to Ro squared times 2 plus Rs over Rp. And then there is this one from the voltage gain equation, which tells us that Rs-Rp is equal to this big quantity 1 minus AV times Rp-Ro minus AV-Rs-Ro, all divided by AV. Now, I can set these two equations equal to each other, which gives us this lovely thing. Now, when I do just a little bit of work, it becomes this, which will help us to simplify it. Now, let's simplify it. Without going through all of the process, this gives me this lovely equation. We have 0 equals 1 minus AV times Rp squared minus AV-Rs-Rp minus 2AV RO-Rp minus AV-Rs-Ro. But we have a problem. Notice that we end up with the same miscreant term in the middle of this equation too. Now what do we do? Well, the answer is simple. We just replace it with one of the Rs times Rp equations we had already come up with. Now, I chose the one based on the voltage gain version. And this gives us this massive looking equation. Now, all we have to do is simplify this. After spending a little effort to simplify this equation, amazingly, I end up with an equation for the parallel resistor Rp, which looks like this. Rp is equal to Ro times the quantity 1 plus 2AV over 1 minus AV. Wow! Now that we have an equation for Rp, we need to create an equation for the series resistor Rs. So how are we going to get an equation for the series resistor Rs? Well, I'm going to take one of the equations for Rs times Rp and solve it for Rs. I will choose the one that came from our Ro equation because, well, it's a much simpler equation to work with. So I'm starting out with this equation. And after a little rearranging and simplification, I get this equation for Rs, where Rs is equal to 2Ro squared times Rp, all divided by Rp squared minus Ro squared. We now have the two equations we need for the resistors needed for the attenuator given the voltage gain and the system impedance. One for the parallel resistor, Rp, and one for the series resistor, Rs. So, there is the whole mathematical process without the nitty-gritty process of simplification. If you found this video helpful, please click on the like and subscribe. Thank you so much for watching. Until next time, Toodle-Oots.